Chapter 10, Carboxylic Acids and Derivatives. Introduction. Carboxylic acids are widely used in our daily life. For example, ethanoic acid in vinegar and butanoic acid in butter. And esters are responsible for the taste and the smell of the most fruits and flowers. For example, isomerism acetate gives the taste of banana. Ethyl acetate gives the taste of pear, and phenol ethyl acetate gives the smell of rose. This chapter is formed of two parts: carboxylic acids and derivatives of carboxylic acid. Now we will see first part, carboxylic acids. One, definition. Carboxylic acids are compounds that contain one or more carboxyl group, COOH or C double bond O single bond OH. Carboxyl group is the combination of two groups. This is the carboxyl group, C double bond O single bond OH. It's formed of two groups. First group is the carbonyl group and second group is the hydroxyl group. Its name is derived from the name of these two groups. Carb from carbonyl and oxyl from hydroxyl, then its name becomes carboxyl group. A monocarboxylic acid is an organic compound that contains only one carboxyl group. We have dicarboxylic acid, tricarboxylic acid, and so on. Our study is only about monocarboxylic acid. Its general formula is RCOOH or RC double bond OOH. General molecular formula. We take an example. Ethanoic acid, CH3COH, is an example of an open chain saturated monocarboxylic acid. Its molecular formula is we have 2 carbon atoms, C2, and 3 plus 1, 4 hydrogen atom, H4, and 2 oxygen atoms, O2, C2H4O2. In general, number of carbon atom is represented by N, and number of hydrogen atom by 2N plus minus. Okay, in this case, N equal 2, 2N equal 4, and number of hydrogen equal 4, then we don't need to add or subtract any number. Therefore, the general formula is CnH2nO2. This is the general formula of saturated. We have no double bond between carbon atoms. And non-cyclic, we have no cycle in the carbon chain. And monocarboxylic acid, one carboxyl group. Therefore, to memorize the general molecular formula of an open chain or non-cyclic saturated monocarboxylic acid is CnH2nO2. The molar mass in terms of N is carbon, molar mass of carbon 12 times N number of carbon, 12N, and hydrogen 1 times number of hydrogen to N, 2n. Oxygen 16 times the number of oxygen 2, 2 times 16. Therefore, the molar mass in terms of n equal 14n plus 32 gram per mole. If we are given the percentage by mass of any element of the carboxylic acid, carbon or hydrogen or oxygen, we can determine its molecular formula based on the relation percentage by mass of carbon over 12n equal percentage of hydrogen over 2n equal percentage oxygen over 32, 2 times 16, equal 100 over molar mass, which is 14n plus 32. But if we are given the percentage by atoms or by mole of any element of the carboxylic acid, we can determine its molecular formula based on the relation percentage carbon over number of carbon atoms n equal percentage hydrogen over number of hydrogen atoms to n equal percentage oxygen over 2 number of oxygen equal 100 over total number of atoms or atomicity of carboxylic acid, which is 3n n plus 2n plus 2, 3n plus 2 is total number of atoms in the carboxylic acid. Application 1, we are given the percentage by mass of carbon atoms in an open chain saturated monocarboxylic acid 48.65. We need to determine its molecular formula. Take your time to solve this application, and after that the solution of application 1. First, we should write the general molecular formula of an open chain saturated monocarboxylic acid is CnH2nO2. Then we calculate the molar mass in terms of n equal 14n plus 32. We are given the percentage by mass of carbon, then the relation becomes percentage by mass of carbon over 12n equal 100 over molar mass. Molar mass equal 14n plus 32. We replace it by 14n plus 32 and percentage by mass of carbon by its value. By mathematical calculation, cross multiplication, we can deduce n, which is equal to 3. Therefore, the molecular formula of this acid is C3H2 times 3, 6O2. Nomenclature of carboxylic acid. According to IUPAC rule, the systematic name of a monocarboxylic acid is derived from the name of the alkane having the same number of carbon atoms in the main chain. But we replace the final E of the alkane by the ending oic and we add the word acid. Alkane plus oic acid, the name, we replace E by oic and we add word acid, the name becomes alkanoic acid. Example: HCOOH, methanoic acid. Methane is the name of alkane formed of 1 carbon. We replace E by oic and we add acid, methanoic acid. 2 carbon, ethane, we add oic acid, ethanoic acid. 3 carbon, propane, propanoic acid. Benzene with COOH or C6H5COH. When the functional carbon is directly connected to benzene, to the cycle C6H5, then C6H5 or C6H6 is takes the non-systematic name benzene. The name of the acid is derived from the non-systematic name of C6H6, which is benzene. We add oic acid, then the name becomes benzoic acid. In case of branched monocarboxylic acids, the functional carbon, the carbon of carboxyl group, is the carbon number 1. For example, in this case we have the main chain formed of 4 carbon atoms and we have metal as alkyl group. The alkane formed of 4 carbon is butane. Then the name becomes butanoic acid, and we have methyl on carbon 1, 2, 3. The functional carbon is the carbon number 1, 2, 3. 3-methyl butanoic acid is the name of this acid. 3-methyl butanoic acid. Application 2. Give the systematic or IUPAC name of the following compounds. Take your time to solve this application. The solution. First, we determine the main chain, the longest carbon chain formed of 1, 2, 3, 4, 5. 5, that means pentanoic acid. And we have 2-methyl dimethyl. This is the carbon number 1, 2, 3, 4. 3, 4 dimethyl pentanoic acid is the systematic name of this carboxylic acid. The other example, CH3 2 times CH, C2H5, CH2COH. When we have CH is connected, CH3 2 times CH, that means this CH, this carbon is connected to two CH3 groups. First CH3 on the line and second CH3 as branch. The main chain is formed of 1, 2, 3, 4, 5 carbon pentanoic acid. We have ethyl group and methyl group. Ethyl on carbon 3 and methyl on carbon 4. We write ethyl before methyl, E before M, alphabetic order of alkyl groups. The name becomes 3-ethyl 4-methyl pentanoic acid, the systematic name of this carboxylic acid. C6H5CH2COH is connected to C6H5 is connected to the carboxylic acid. This is the main chain formed of 2 carbon ethanoic acid. And C6H5, when it is an alkyl group, it's called phenol, derived from the systematic name of benzene, which is phen. Phen, the alkyl group, is phenol. Phenyl ethanoic acid, not methanoic. Correction. Phenyl ethanoic acid. Isomerism. C4H8O2 has 2 carboxylic acid isomers, not 3. 2, which are first 4 carbon atoms on the line, straight chain, which is butanoic acid, and second we eliminate 1 carbon from the carbon chain and we make it as alkyl group on the carbon number 2. The formula becomes CH3CH, CH3C double bond O, single bond H, which is 2-methyl propanoic acid. Application 3, we have C5H10O2 carboxylic acid. We need to write the isomers of carboxylic acid of formula C5H10O2. Take your time to write these isomers, and after that we see the solution of application 3. First, the straight one formed of 5 carbon pentanoic acid. Then we decrease the carbon of the main chain 1. The main chain becomes formed of 4. The fifth carbon can be connected to carbon number 2 or carbon number 3. Then we obtain two isomers of chain of 4. The first one, we connect the methyl group to carbon number 2, 2-methyl butanoic acid. And the second one, we connect the methyl group to the carbon number 3. We change the position of the methyl group. We obtain this isomer, 3-methyl butanoic acid. The fourth isomer, we decrease the number of carbon, also 1 carbon, and the chain becomes formed of 3 carbon. 2 carbon are 2-methyl on carbon number 2. 2,2-dimethyl propanoic acid. These are the isomers of C5H10O2 as carboxylic acid. Now, physical properties. As in all organic compounds, when the molar mass increases, the boiling point of the organic compound as the carboxylic acid increases. Now, special case in carboxylic acid, the formation of dimers. Dimers is the result of hydrogen bond between two molecules of carboxylic acid. This is the dimer of 2 carboxylic acid. Oxygen, the bond between carbon and oxygen is polar, and oxygen is the negative pole, has negative, partially negative charge. And the oxygen and hydrogen, the bond between O and H in OH group is polar, and H is the positive pole of the bond and oxygen is the negative pole. The same for the second acid. H is the positive pole and O is the negative pole. Positive and negative attract each other, forming one hydrogen bond and the other hydrogen bond. Two hydrogen bonds forming what is called dimer. Dimerization of carboxylic acid increases its boiling point because we need extra energy to break down the strong hydrogen bond in case of carboxylic acid, which increases the boiling point of carboxylic acid compared to other organic compounds having same molar mass, as we will see in the following video showing the variation of boiling points of carboxylic acid. When the molar mass increases, boiling point increases.
The boiling points of carboxylic acids are noticeably higher, though, than those of other organic compounds of comparable molar mass, including alcohols and aldehydes.
Then the boiling point of carboxylic acid is higher than that of alcohol and aldehyde. This is the dimerization of carboxylic acid.
Which involves attraction between positively charged hydroxyl hydrogen atoms and negatively charged carbonyl oxygen atoms. In every dimer, two molecules of acid are linked together by a pair of strong hydrogen bonds. Additional energy is required to break the dimers into the single molecules that occur in the vapor phase. For example, the boiling point of ethanoic acid is much higher than that of propan-1-ol, which is
In case of carboxylic acid, we have two hydrogen bonds. In case of alcohol, we have one hydrogen bond, so that the boiling point of carboxylic acid is higher than that of alcohol of same molar mass, and higher than that of aldehyde because the hydrogen bond in aldehyde is weaker than that in alcohol and in that of carboxylic acid. Now, chemical reactions. Reaction with water. Carboxylic acids are weak acids that react partially with water according to the general equation. RCOH plus H2O give RCO minus plus HO plus. Weak acids, acid in general, are donor of H plus. H plus to H2O, we obtain H2O plus. And the acid is transferred into conjugate base RCO minus, which is carboxylate ion. Reaction with strong bases. Carboxylic acid reacts with strong base according to the complete reaction of equation. RCOH plus HO minus give RCO minus plus H2O. HO minus is strong base. Acid donor of H plus to the base HO minus to give H2O, and the acid is transferred into its conjugate base RCO minus. Reaction with strong base. Remark: the conjugate base RCO minus of the carboxylic acid is called alkanoate ion. Don't forget to add the word ion. Alkanoate is not accepted alkanoate ion. For example, HCO minus from methane, methanoate from methanoic acid, we replace oic by OAte and acid by ion. Then methanoate ion. Don't forget to add the word ion. CH3CO minus ethanoate ion. Ethanoic acid becomes ethanoate ion. Reaction with some metals. Carboxylic acids react with the more reducing metals than the dihydrogen than H2, such as Fe, Zn, Mg, Al, and so on, to give salt with metal alkanoate and dihydrogen gas H2. All the metals that are below the couple H plus H2 in the electrochemical classification can react with carboxylic acid. General reaction with Mg, RCOH, 2 RCOH plus 1 Mg atom. Mg is transformed to its ion Mg2 plus. 2 plus needs 2 minus, so that we need 2 carboxylic acid, and 2 H plus are reduced into H2. Reaction with carbonates. Carboxylic acid also react with carbonates to give salt, carbon dioxide, and water according to the equation, with calcium carbonate as example. CaCO3. Ca is Ca2 plus, 2 plus with 2 minus, 2 RCO minus. CO3 2 minus with 2 H plus give the carbonic acid H2CO3. H2CO3 is unstable. It decomposes into carboxylic into CO2 and H2O. Then the final product are salt, calcium alkanoate, CO2, and H2O. This is the first part of the chapter 10, carboxylic acid.